Good morning, dear students. The Department of ECE welcomes you to the lecture series on Computer Communication Networks Laboratory. The subject code is 17 ECL 68, 15 ECL 68, 6 semester A, B and parallel batch. The part B, the experiment number 10. And this is presented by A.V. Kolaki, Assistant Professor, Department of ECE, KLS, VDIT, Haria. The experiment number 10 definition: implement a Dijkstras algorithm to compute the shortest routing path. We discussed in the experiment number 9, that is distance vector algorithm. In that we are finding one shortcoming in that. So to overcome that shortcoming, we are discussing this Dijkstras algorithm. So let us begin. What is the shortcoming we noticed in the distance vector algorithm? Uh, the two node instability, the problem we are noticing in the distance vector algorithm, and that we call it as a count to infinity. If a link is broken, then the cost becomes infinity. Every other router should be aware of it immediately, but in distance vector routing this takes some time. So due to this, the count to infinity problem will be arises in the distance vector algorithm. So let us take one example and try to understand what is that count to infinity problem. Let us consider this figure. In that, at the beginning both nodes A and B know how to reach node X. The B can reach the X via A and A can directly reach the X. And there the node table or a router table is given as it is A can reach X with 1 cost and B can reach X with a cost of 2 with the intermediate node as A here. So this is the beginning before failure of the link. So this is what the scenario. So let us see what happens next now. Now in this, suddenly the link between A and X fails. Node A changes its table. If A can send its table to B immediately, everything is fine. But here in the distance vector algorithm, it is taking some time to share its updated table. The A will be sharing its updated table to the B with a little bit delay here. So because of that, the problem will be rises. Now you can note down in this figure that there is no link between the router A and a X. So that is get failed now. That link is get failed. So therefore the cost of reaching that becomes very suddenly higher because A can't reach X now. So that's why it has made it table as the cost of reaching A to X is 16, or you can call it as the infinite. Then this table we are not sharing with B immediately. So now what happens next? Let us see that. The system becomes unstable if B sends its forwarding table to A before receiving A's forwarding table. Node A updated and receives the update, and assuming that B has found a way to reach X, updates its forwarding table. Now the problem is that here the instead of sending A its updated table to B, the B has forwarded its table to A now. Now the A will be thinking that the B might have computed any other alternative route to reach the X here. So whenever the B shares its table, when that B shares with A here, then now A will be updating its table, thinking that B has an alternative route to reach the X here. So therefore, it makes it updates its table as A to X with a cost of 3. I can reach the X with a cost of 3 because the cost of A to B is 1 is there. So therefore it has updated its table as I can reach X with a cost of 3 here. Now A sends its new update to B. The B thinks that something has been changed around A and updates its forwarding table. So when that A get updated its table and that table will be forwarded to B now. Now B thinks that something might have changed with the A's table, so that's why his table will be updated now. Now I need to update my table according to that. So therefore, so B updates his table like I can reach X with A with a cost of 4 because it has sent 3 costs and the distance between me and A is 1 is there. So therefore it is updating its B table as I can reach with a cost of 4 here instead of 2 earlier. Next, so like that the B updated table will be forwarded to A and A will be updated for table will be forwarded to B. So like that the packet will be the bounces between A and B and A here. So that's where the process will be get continuous. And finally now the cost of reaching X increases gradually until it reaches infinity. Then A and B know that X cannot be reached. The system is not stable. Node A thinks that the route of X is via B, or the node B thinks that the route to X is via A. The packets destined for X will bounce between A and B, creating two-node loop problem. So this how a count to infinity problem will be occurs in the distance vector algorithm. To overcome this, let us discuss about the link state routing. A routing algorithm that directly follows our discussion for creating least cost trees and forwarding tables link state routing. Sometimes it is also called as LS routing. This method uses the term link state to define the characteristic of a link or a edge that represents a network in the internet. In this algorithm, the cost associated with an edge defines the state of the link. The links with lower costs are prepared to the links with higher costs. If the cost of a link is infinity, it means that the link does not exist or has been broken. So this is what the link state routing algorithm. So let us will implement this in the Dijkstras algorithm and we'll continue this in the next slide now. Let us take one example for a link state database. The link state database, it's a collection of states for all links The link state database can be represented as a two-dimensional array or a matrix in which, like this, in which the value of each cell defines the cost of the corresponding link. There is only one LSDB, that is link state database, for the whole internet. Each node needs to have a duplicate of it to be able to create the least cost trees. The least link state database is mentioned here. The A to A is 0. The self node reaching is, the cost is 0. Then A to B, because A is directly connected to B here, so the cost of reaching A to B is 2. And then the cost of reaching C, the C is not directly connected with A, so therefore the cost of reaching C will be infinite. Then A to D, the D is also directly connected with A, so therefore the cost of reaching A to D is 3 is there. And next A to E, A is not connected with A directly, so therefore the cost of initially the reaching E will be infinite, even for F, even for G. So this way the weighted graph, the given weighted graph will be put in the link state database like this initial condition. Whenever we get a weighted graph, and by referring to that, this link state database will be initialized. It will be looks like this. The figure, the least link state packets created and sent out by each node to build link state database. How each node can create this link state database? They create this by flooding the packets. Each node send link state packet to all its immediate neighbors to collect two pieces of information from the neighboring node. That pieces of information are the identity of the node, the cost of the link. By sharing the link state packet, they exchanging these two information. Which node is my neighbor and what is the cost of reaching that node here, the link cost. Let us take another example and try to create that the link state database for that. This is what the same weighted graph what I mentioned in the last slide, that is what I considered here. There are A, B, C, D, E, F, G. The nodes or routers are present in this weighted graph, and these nodes or routers, they are exchanging their link state packet to create their link state database. How it will be created, let us discuss. When a node receives an LSP, it compares the LSP with the copy it may already have. The node checks the sequence number in both LSP to know which one is old, and that will be discarded it and keep the new one. So this is what the system we are following to create the link state database. Whenever the nodes they are exchanging their link state packets, that time the node the receiving node will compares whatever the link state database or information I'm having, which one is the older one. By referring its sequence number, it discards the old one, and whatever the new copy is there, the that copy will be retained. That's how it updates. Then node sends a copy of it out of each interface except the one from which the packet arrived. From which node we are receiving that packet, leaving that node, the remaining interfaces, how many interfaces we are having, there we are translating that. We are sending that link state packet to update my neighbors. This guarantees that the flooding stops somewhere in the network where a node has only one interface. Each node creates a comprehensive link state database. This link state database is the same for each node and shows the whole map of the internet. In other words, nodes can make the whole map if it needs to using the link state database. Let us see that how that the link state database is creating and sending its link state packets to the neighboring nodes here. The node A, which receives a packet from B and D, and it creates the link state database. The B sends that I can reach you, I am B, and I can reach you A with a cost of 2. Similarly, D says that I am D and I can reach you with a cost of 3. Similarly, the B receives the message from its interfaces. A sends to B, E sends to B, and C sends to B here. So A can reach B with a cost of 2 because the B will comes to know that with this link state packets, who are my neighbors? What is the node identification will be comes to know when the link state packets will be get shared by the neighboring nodes to the B. So therefore the B's neighboring nodes are A with a cost of 2, it is available, and my another node is the neighboring node is C with a cost of 5, and my another neighboring node is E with a cost of 4. I can reach E here. Like that for C, like that for D, like that for E, F, and G. Let us compare the link state routing with the distance vector. What is the difference? In the distance vector routing algorithm, each router tells its neighbor what it knows about the whole internet. Whereas in the link state routing algorithm, each router tells the whole internet what it knows about its neighbors. The neighboring details will be get shared here, and here the neighbors tells what is the whole network internet here. That is the major difference between that. Let us discuss about the Dijkstras algorithm and how this algorithm works. To create a least cost tree for itself using the shared link state database, each node needs to run the Dijkstra's algorithm. By making use of this algorithm, they can share the link state database. The Dijkstras algorithm, it goes like this. The node chooses itself as the root of the tree, creating a tree with a single node and sets the total cost of each node based on the information in the link state database. The node selects one node among all nodes not in the tree which is closest to the root and adds this to the tree. After this node is added to the tree, the cost of all other nodes not in the tree needs to be updated because the paths may have been changed. The node repeats the step 2 until all nodes are added to the tree. So this is what the algorithm we are following in the Dijkstra's algorithm. First of all, we need to have a root node. Then by considering the root node and the whatever the information I'm having, the link state database, so I'm keep on adding the nodes or I'm keep on adding to the tree, my tree to the root which are neighbors to me, and the cost of reaching those neighbors should be minimum least. So that's why I keep on adding one another nodes to my tree till I cover all the nodes from the source node or a root node. In this I'm defining the source node, and next here I'm adding the tree. Now I'm keep on adding my tree which are my neighbors, and how I can keep on add my the neighboring nodes to my tree. So here we are reading the total, the cost matrix of my given the weighted graph, and in this part continuously understand who are my neighbors and which is having a least cost, and that is what we are keep on following and we are keep on updating. So this how this Dijkstra's algorithm it works. So let us discuss how that least cost tree will be we are creating. The figure shows the information of the least cost tree using Dijkstra's algorithm. We need to go through an initialization step and 6 iterations to find the least cost tree. This is my source node, that is A is the source node. Let me elaborate you that what are the meanings of that with the legend here, then we can continue that. The black node we are representing as a source node, and blue we are the node with the path, and white color the node not yet in the path, and dotted arrow is representing it's a potential path, and the solid arrow is representing the path. So initially I am at the 8th node, that is source node. The cost of reaching A itself is 0, and the A's neighboring nodes are B and D. So therefore the potential path will be either this, either this. So this is these two nodes, the B and D, are not yet in the path. They are not a part of the tree right now. So now it analyzes, it uses that Dijkstras algorithm. So I can reach B with a cost of 2. There is no other alternative route to reaching this. So via D and again coming E, and this is becomes somewhat costlier, and even I don't know what is the cost of reaching even E also right now here. So therefore it adds the B is my immediate neighbor node with a cost of 2 is there, so that will be get added. Then once the B adds its this node as a tree to this root, then it computes what are its immediate neighbors, the B's immediate neighbors. The B's immediate neighbors are, one is C with a cost of, because B to C is 5 is there, and A to C becomes 7, and B to E is, the cost is 4 is there, and A to E is 6. So that's how it is mentioned. And then it finds the A's immediate node is 3 is there, because here 6 and coming back it is too costlier. So therefore the A will now considers my next, the node will be in my tree, that is D, because I can reach D with a cost of 3. Then after adding that, it then continues to add its trees with the help of B, because if I want to reach from via D to E here, that will be much costlier compared to via B here. So therefore it considers B as my next node to reach either C or E here. So therefore it confirms out of these two journeys, A to reaching C or A to reaching E, because A to C is 7 is there, it is, the cost is high compared to A to E. So therefore it confirms now my next node will be E via B with a cost of 6. When these two nodes are added in the path, then its immediate neighbor nodes are now, one is C is left, another immediate node is F, and this is already marked, we are not going back here. Now the cost of reaching C and F now, which is minimum in these two, that is C is the minimum. So therefore in the next, the the node will be considered in the tree is C. I can reach A to C via B with a cost of 7. Then from this it computes its immediate node is 10. I can reach 10 from A with a cost of 10 is there here. And coming from this node, that is E node, with what cost I can reach F, that is A to F I can reach with a cost of 8, whereas via C the cost of reaching F will be somewhat costlier. So that's why I'm not considering this potential path. I'm considering E to F path with a cost of 8 is there. So therefore I am including the F in my tree now, the root tree. So therefore the cost of reaching F is with a cost of 8. Then the cost of reaching via F, it becomes 9, and already I studied here with a cost of with a node, intermediate node as C, I can reach G with a cost of 10. So comparing via C and via F, the least cost will be via F here. So therefore that is the path, this potential path we considering, and that's how even the G node is also get added to the root node. So this how the root node A is now it is able to reach all the nodes of the given graph. So this how these are the various paths that will be get selected, and that will be the data link state database will be created or generated like this. The A to D with a cost of 3, A to B with the cost of 2, A to E via B with a cost of 6, A to C via B with a cost of 7, and A to F via E with a cost of 8, A to Z via F with a cost of 9. Now let us move to how can we implement this in the code block. I already mentioned in the earlier uh, my video how to start this kind of icon you are finding in your uh, desktop screen or a laptop screen. You can double click on that. When you double click on that, you find the like this window. This is the code block window. In this code block window, you need to go to file. In the file, you can find a new, and under that, when you click the new, you are finding an empty file. So you can select this empty file. When you select the empty file, you are finding like this space. Now here you need to write down the algorithm or a code, C code. You can write down, and once you complete that typing work, then you need to save that the file. So then again go to file and select save file. When you select save file, you will get this option, and here you can create your folder, or you can give the file name. Under that folder you can give your file name for this, the Dijkstras, the program, with the extension as .c, and then you can click on save button. After saving that, we need to now compile and run. To compile or run, first we need to go to the option called as a build option. So when you go to the build option, there you can select a build. So once you select a build option, you can find a compile, or you can use the shortcut key as Control Shift F9 button to compile your the file. After compiling that, if this program consists any errors, then that errors will be get highlighted here, and those errors has to be get cleared. After clearing all the errors, again you can compile your file. After compiling, then again go to the build, and the next to compile is run is there. You can click on run, or even you can make use of the shortcut key as the control plus F10. So that will be runs your code, and after running that, so you are going to get this kind of another pop-up window. So here, as per your program, you need to keep on enter your values. For the Dijkstra's values, I am asking because I need to collect how many vertices are there, how many nodes are there in my um, the given graph here or considered graph here. So that is the number of vertices I need to provide, our nodes has to be provided. After that, it will next ask enter the cost matrix. What is the matrix of that? The graph here. And after that, it will ask me what is the source node, which node you want to consider as a source node. I need to I need to give that source node. So first, let me go that cost matrix. So I am entering my cost matrix like this. I'm considering this as my the graph. weighted graph, and according to this graph I am entering the cost matrix. This is the node number 1, node number 2, node number 3, node number 4. So I can reach 1 to 2 5, 1 to 3 10, and next 2 to 4 11, 2 to 3 4, and 4 to 5 3 to 4 with a cost of 5 here. So this is the matrix I considered, and these are the weights or a cost. I'm taking it some random values for that. You need to have this complete picture with you, and accordingly you can enter that cost matrix. 1 to 1 is 0, 1 to 1 is 0, 1 to 2, 1 to 2 with a cost of 5, 1 to 3 with a cost of 10, 1 to 4. Can I reach 1 to 4? I can't reach 4 because the 4 is not directly connected to the node 1. So therefore I'm mentioning triple line. Triple line is nothing but it's an infinite. Similarly 2 to 1 is 5, 2 to 2 is 0, 2 to 3 is 4, then 2 to 4 is 11 because the second node will reach all the remaining 3 nodes. So therefore it can reach all the other nodes here, even 3. So this way, the 3 node, fourth node, what are the cost with reaching the its other nodes will be, we are entering as a cost matrix. Once I enter that, next it will ask, my code will be asking that what is the source node? What is the source node? I'm selecting my source node as 1. When I give all these inputs, when I enter it now, I'm going to get this kind of least cost tree. The Dijkstras algorithm will provide me a least cost tree for me. From the vertex, that is from the source node 1, how I can reach all other nodes. So that is what we are computing in the Dijkstras algorithm. From the source node 1 to the destination node as 2, I can reach directly with a cost of 5. With a cost of 5 reaching it. Then 1, 2, 3. Can I reach directly? Yeah, you can reach it. But the cost of that is 10 is there. So that is somewhat costly here. But what is the alternative route I can reach? So 1 to 2 I can go, from 2 to 3 I can also come here. The cost of that is 5 plus 4 is 9 is there. Compared to the direct path via 2 node, I can reach the destination node as 3 with the cost as 9, and that is what it is computed. 1 to 3, that is destination node 3, I can reach with a cost of 9. Then 1 to 4, my destination node is 4 now. How I can reach it? What are the paths I may be computing here? I may go like this way, and this way, because I can't go like this, because reaching the third node is 9. That is via 2 only I can reach. That is the cheapest cost here. And via this one, this is somewhat costly here. So that's why I'm not picking this. I need to move now this way, or I need to move now this way here, which is the minimum. That is what we need to consider. If I go like this now, what is the cost of that? 11 plus 5 will be 16. What is the cost of this? From this to this point, the 9 plus 4, it is 14. So therefore, the cost of reaching fourth node via 3 node is will be the best route, or the least cost, rather than reaching via 2 here. So therefore I mentioned here. So 1 to 4 I can reach with a cost of 14. So this way even you can take another the the graph with the weighted graph, and you can enter the cost matrix for that in the code here. In this the value you can enter, and you can select any root node here. So I have selected here 1. Even you can select root number 2 as a source node. The router 3 you can select as a source node. So like that you can choose the other nodes as a source node, and you try to find out what is the least cost tree we are getting for those nodes. So thank you very much.